Hello everyone, welcome to today's lecture. So in today's lecture, we will do some previous CBSE previous year questions based on the topic relations and functions. Okay, the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of our content may have been generated using generative AI, which is experimental. DPV will be accessible. Okay, let's start. First question says, this was asked in the year 2022. The question says, a relation R is defined on N, right? We have defined the relation R, which is defined on N, which is natural number, right? Which of the following given relations out of the four options is the reflexive relation, right? We have to discuss whether the given four options, out of which relation given is reflexive or not, right? Okay. So what is the condition of a relation to become reflexive? We know that the condition for a relation to become reflexive is, suppose A should belongs to set A for all A belongs to A, right? Clear? Suppose you have a set A having elements 1, 2, 3. Got it? So for reflexivity, the relation R should have all the elements 1, 1. Got it? 2, 2. Isn't it? 3, 3. Got it? These three ordered pairs must contain the set, must contain the relation R. Then we can say that it is reflexive, right? Okay. So out of the given four options, which will be reflexive, we will discuss now, right? You have 10 seconds to solve or think about this question. After that, we will discuss the solution part, okay? Yes, some students is commenting. Okay. Very good. Option C will be right. Okay. Yeah. C. Let's discuss solution. The question was a relation R on defined on N. You must see that the relation is defined on a natural number N, right? Got it? Which of the following is the reflexive relation? So answer is C. Very good. Answer is C, which is relation R is equal to xy such that xy is a square number, right? And xy should belong to natural number. Let's see. Okay, let's move to the solution part. See, a relation R is reflexive. We know that. We have discussed the condition for reflexivity. A relation R is reflexive if xx should belongs to R, right? If we have defined a relation R, then xx must contain in the set R, right? For all x belongs to natural number. If this condition will be satisfied, then we can easily say that the relation we have defined is reflexive relation, okay? So let's check each options. Option A says x is greater than y. So x will be for reflexivity, xx should contain in the set. Therefore, we can say that x should be greater than x, which is not true, right? Which can never be true, right? 1 is greater than 1. Is it possible? No, right? 2 is greater than 2. Is it possible? No. Got it? So any number cannot be greater than itself, right? Any number is equal to itself. Therefore, x greater than x is never true, right? So it is not reflexive. Okay. Let us move to the option B, which says that x minus y is 0, right? Clear? So x minus x, like x minus y should be equal to 10. But for reflexivity, x and x should contain the relation. Therefore, x minus x is equal to 0, which is not 10, right? Obviously, 0 is not equal to 10. So it is not reflexive. Got it? So option B is also wrong. Now let's move to the option C. Option C says xy is the square number, right? Xy is the square number. So xy is the square number, then xx must lie in the relation R. So x into x, which is x square is always a square number for any x, right? So this is reflexive. Therefore, option C is right. Let's also discuss option D. D was x plus 4x is equal to 5x, right? 5x equal to 10 gives x equal to 2, right? So this is true only for x equal to 2, right? But not for all the x belongs to natural number, right? This is only true when x is equal to 2, right? Okay. So for it is not true for all x. Therefore, we can say that the option D is also not reflexive, right? Therefore, overall, we can say that by conclusion is option C is the reflexive relation, right? Okay. Hope you understood the like condition of the reflexive relation. Okay. Okay. Let's move to the next question. Next question says the number of equivalence relations in the set 1, 2, 3 containing the elements 1, 2 and 2, 1 is. This question is also asked in the year 2022 and the options are 0, 1, 2, 3. We basically have to find the number of equivalence relations in the set 1, 2, 3. Equivalence relations from the set 1, 2, 3 having element 1, 2 and 2, 1 must contain, right? Okay. So what is equivalence relation? What are the conditions of equivalence relations? The conditions are the relation must be reflexive, right? The relation must be reflexive. Got it? Symmetric and transitive. Clear? All the three conditions must be satisfied for a relation to become equivalence relation, right? Transitive. Got it? So for reflexive, what is the condition? For reflexive, AA should belongs to relation R for all A belongs to A. Got it? Therefore, like for reflexive, 1, 1, 2, 2 and 3, 3, all the three elements or all the three ordered pairs must lie in the relation R. Got it? Any other ordered pair can lie, but 1, 1, 2, 2 and 3, 3 must lie. Got it? For the relation to become reflexive. Now for symmetric, what is the condition of symmetricity? If A B belongs to R, if AB belongs to R, AB belongs to R, this imply BA must belongs to R, right? BA must belongs to R. Got it? So if 1, 2 is containing in the set, then 2, 1 must contain, right? 2, 1 must contain. If 1, 3 is containing in the set, then 3, 1 must contain. Clear? This is the condition of symmetricity. And what is the condition of transitivity? The condition of transitivity is if AB belongs to R and BC belongs to R, this imply AC must belongs to R. Got it? The condition of transitivity is if AB belongs to R and BC belongs to R, this imply AC must belongs to R. See, you must focus here that whole statement must be satisfied. That is, if AB belongs to R and BC belongs to R, this imply AC must belongs to R. See, if AB and BC does not belongs to R, if AB and BC does not belongs to R, then we are not. Then it is not guaranteed that AC must belongs to R, right? Only AC should belongs to R if AB belongs to R and BC belongs to R, right? Clear? So this is the condition of transitivity. So for equivalence relations, all the three conditions must be satisfied. So we must have to form the set of relations in which all the three conditions must be satisfied for the relation to become equivalence relation. Got it? So you must think in this way, right? Okay, you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let's move to the solution part. The question was the number of equivalence relations in the set 1, 2, 3 containing the elements 1, 2 and 2, 1, right? The set must contain 1, 2 and 2, 1. Got it? So correct answer is option C, right? 2, right? There must be only two, there will be only two equivalence relations can be drawn from 1, 2, 3, the set 1, 2, 3, which containing the element 2, 1 and 1, 2, 1 and 1, 2, right? So let's elaborate, right? the solution is, see, total possible pairs. See, we have set, suppose 1 2 3, 1 2 3. We have to define a relation from 1 2 3 to 1 2 3. So how many pairs can we see? From 1 1, got it? 1 2, 1 3. Clear? 1 can be related to 1 1, 1 2, and 1 3. Got it? Now 2 can be related with 2 1, right? 2 2 and 2 3, right? 2 1, 2 2, and 2 3. 3 can be related with 3 1, 3 2, and 3 3. Clear? 3 1, 3 2, and 3 3. So these many ordered pairs can be defined from A to B. Now we have to make the relation in such a way that it becomes equivalence relation, and the relation must contain 1 2 and 2 1. Got it? Okay, let's move. So reflexive means, what was the condition of reflexivity? The reflexive means 1 1 2 2 and 3 3 must lie. Got it? Reflexive means 1 1 2 2 and 3 3 must lie, right? And for symmetricity, see, if 1 2 is lying, 2 1 is T1 will also be present, right? So for symmetricity, 1 2 and 2 1 must lie. Got it? So we can define one relation as, and for transitivity, what can be the condition? If 1 2 is in the relation and 2 1 is in the relation, then 1 1 should also be there, right? And 1 1 is already there if we define the relation with 1 1 2 2 and 3 3, right? So the relation R1 can be 1 2, 2 1, 1 1, 2 2, and 3 3. You can check that like all the conditions of reflexivity, symmetricity, and transitivity is satisfying while making this relation R1, right? Clear? You can say that for reflexivity, 1 1 is lying, 2 2 is lying, 3 3 is lying here. Got it? For symmetricity, if 1 2 is lying, 2 1 is also lying. Got it? 1 2 is lying, 2 1 is also lying. For symmetricity, for transitivity, you can check that. See, 1 1 is lying, 1 1 is lying, and 1 2 is lying. Then what can be what will be the next ordered pair for this become transitive? 1 2 must lie. 1 2 is already there. Got it? So any ordered pair you will check, all the conditions, reflexivity, transitivity, and symmetricity will be satisfied here. So relation R1. So let us try to make another relation which must be equivalent. See, you can see that the smallest relation can be defined is 1 2 2 1, 1 1 2 2, and 3 3, right? Let us define another relation. Try to define another relation. Now, suppose if we add 2 3, right? If we add 2 3 in this relation, then for the relation to become symmetric, we must add 3 2, right? If we are adding 2 3, then 3 2 must be added. Got it? But 1 2 and 2 3 are there, right? See, if we add 2 3, then 1 2 was already there. 1 2 was already there, and we have added 2 3. Now for this to become transitivity, 1 2 is there, 2 3 is there, then 1 3 must be there, right? 1 3 must be there. So we need to add 1 3. Now if 1 3 have been added, then for the relation to become symmetric, 3 1 must be added, right? 1 3 have been added. Then for relation to become transitive, for the relation to become symmetric, 3 1 must be added, isn't it? As we are adding 1 3, so we should add 3 1 also for the symmetricity conditions to be satisfied, right? Okay. So R2 can be defined as 1 2 2 1, 1 1 2 2 3 3. We have added 2 3. So we have added 2 3. So 3 2 must be added. Now if 2 3 have been added, 3 2 must be added. See, 1 2 was there, 2 3 is there. 1 2 was there, 2 3 is 1 2 was there, 2 3 is there. So 1 3 must be there. So we have added 1 3 also. Now if we have added 1 3, then 3 1 must be added, right? So we have added 3 1 also. Clear? So now this can be said that R2 is transitive now, right? Clear? So only two possible relations are there which are equivalents. Got it? No other relations can be defined. You can say that all the elements, like total possible pairs was like 9 ordered pairs, right? And all the 9 ordered pairs have been added in the relation R2, right? So no further ordered pairs can be added. Clear? So only two relations are possible, uh, uh, satisfying all the given conditions, right? For the relation to become equivalence, and 1 2 and 2 1 must be there, right? So only two possible relations are there, right? Okay, let us move to the next question. So next question says a relation R is defined on Z. Z is integer, right? We have defined the relation R on integer Z as A related to B if and only if A is related to B if and only if A square minus 7AB plus 6B square equal to 0. Clear? Then R is, options are reflexive and symmetric, symmetric but not transitive, symmetric but not reflexive, transitive but not reflexive, reflexive but not symmetric, right? So again, I am repeating the conditions of reflexivity, symmetricity, and transitivity. So what was the condition of reflexivity? AA AA should belongs to R for all A belongs to A. Got it? That means if suppose we have suppose if we have said suppose 1 2 3, then for the relation to become reflexive 1 1 2 2 and 3 3 must lie in the relation R. Clear? All the three ordered pairs must lie in the relation R. Got it? For reflexivity, right? This is condition for reflexivity, right? What is the condition for symmetricity? If AB belongs to R, this imply BA must belongs to R, right? If AB belongs to R, this imply BA must belongs to R, right? So suppose if 1 2 is there, this imply 2 1 must be there in the set, right? For the relation to become symmetric. And for transitive, what is the condition? If AB belongs to R, AB belongs to R, and BC belongs to R, this imply AC must belongs to R. Clear? This is the condition of transitivity. Clear? So by options, if like 1 2 is lying and 2 3 is lying, then there must lie 1 3. Clear? Then there must lie 1 3 to for the relation to become transitive. Got it? Right. So we have defined a relation on integers z, right? If and only if a square minus 7ab plus 6b square should be equal to 0, then r which condition will be satisfied by R? Clear? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay. Okay, Tushar, you are saying option A. Let's see. Okay, let's move to the solution part. The question was a relation R is defined on Z as A related to B if and only if a square minus 7ab plus 6b square equal to 0, then R is. The correct option is option D, right? Option D should be the correct, which is reflexive but not symmetric, right? Clear? The relation R will be reflexive but not symmetric. Let us discuss. So let's move to the solution part. So given relation R on Z defined by A related to B if and only if. See, the condition is A square minus 7ab plus 6b square should be equal to 0, right? Let's factor the equation. First, let us factor this equation A square minus 7ab plus 6b square equal to 0. So we will get A square minus 7e plus 6b square can be factored as A minus b into A minus b into A minus 6b, right? A minus b into A minus 6b, which is equal to 0. Got it? So either A equal to b or A is equal to 6b, right? Either A equal to b or A equal to 6b. Got it? So we are getting A equal to b. Any other thing we are getting, it's fine. But A equal to b, A equal to b we are getting. Clear? So the relation will be reflexive. Got it? Clear? The relation will be reflexive. Got it? Because we are getting A equal to B. We are also getting A is equal to 6B, but it's fine, right? Because A equal to B must be satisfied, right? A must lie. A must lie. Clear? For all A belongs to A. Got it? Any other things is lying, it is fine. Got it? But A must lie. Clear? Therefore, A is equal to B is coming, so it will be reflexive. Reflexive. What is the condition of reflexive? For any A is equal to A holds. A equal to A is holding, so R is reflexive. Got it? Now let us check for symmetric. If A related to B, that is A is equal to B, so B is equal to A. Clear? So for this condition, it is symmetric. But if A is equal to 6B, then B is not equal to 6A, right? If A is equal to 6B, then B is not equal to 6A. Then for B related to A, we need B is equal to 6A, which is not generally true. Clear? It is true only in one case. The case is A is equal to B equal to 0. Got it? So it is not symmetric. Got it? Clear? So it is not symmetric. You might have confusion that in reflexive, we were getting two conditions, A equal to B or A equal to 6B. But it is reflexive. But for symmetric, we are getting two conditions, A equal to B and or A is equal to 6B. Then why it is symmetric but not reflexive? Why it is not symmetric but reflexive? See, the condition for reflexive is that A must lie. Other than this, anything is lying, it is fine. But A must lie. So A is equal to B is happening. It doesn't matter whether A is equal to 6B also, right? Clear? A is equal to B is happening. But for symmetricity, for all the relations, if B is lying, then B must lie, right? Suppose 1 2 is lying, then 2 1 must lie. Got it? 2 1 must lie. But here you can say that A is equal to 6B is happening, but B is equal to 6B. 6A is not happening. Clear? So it is not symmetric. Got it? Thus R is not symmetric. So we can say that option D is correct, which is the relation R we have defined is reflexive but not symmetric, right? Clear? Okay, let us move to the next question. Next question says, if relation R is defined as xy such that x plus 2y is equal to 8 is a relation on N, write the range of R. We basically have to find the range of R, right? This question have been asked in year 2014. So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. See, first we can discuss what is domain and range. It is defined a relation on all natural numbers, right? So domain is x. X is domain, right? And y is range, right? Clear? So for every x, we basically have to find the value of y. Got it? Clear? For every x belongs to natural number, what can be the value of y? We need to find that. That will be the basically range. Okay. So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. The question was, if R relation is basically xy such that x plus 2y is equal to 8 is a relation on N, we basically have to find the range of R, right? So let's move to the solution. It is given that relation R is defined as xy such that x plus 2y is equal to 8, where xy belongs to natural number, right? To find the range, solve for y in natural numbers, right? We must solve for y. So it is given that x plus 2y is equal to 8. Therefore, 2y can be written as 2y is equal to 8 minus x. Therefore, y is equal to 8 minus x by 2, right? Y will be equal to 8 minus x by 2. So for y to become natural number, 8 minus x must be positive and even, right? For y to be a natural number, clear? 8 minus x must be a positive and even number, right? So possible values of x are 6, 4 and 2. Clear? Clear? 6, 4 and 2. See, the conditions must be satisfied. For any value of x, y must be natural number, right? Y must be natural number. Clear? So 6, 4, 2 must lie. See, 0 is not natural number, right? You cannot put 0 in place of x. Clear? You cannot put 0 in place of x, right? So corresponding values of y will be, for x equal to 6, y is equal to 1, right? For x equal to 6, y equal to 1. For x equal to 4, y equal to 2, right? For x equal to 4, y will be equal to 2. And for x equal to 2, y is equal to 3, right? So range of R is basically 1, 2 and 3. Will be 1, 2 and 3. Got it? Range of R is basically 1, 2 and 3. Okay. Let us move to the next question. The next question says, let R be the equivalence relation in the set, right? R is basically the equivalence relation in the set. A is equal to 0, 1, 2, 3, 4, 5, given by the relation R is given as R is equal to AB, such that 2 divides A minus B, right? 2 divides A minus B. We basically have to write the equivalence class of 0, right? We basically have to write the equivalence class of 0. This question was also asked in 2014, right? Clear? Okay, again you have 10 seconds to solve or think about this question. After that, we will discuss the solution part, right? Okay. Okay, let us move to the solution part. The question was, the set A was given as 0, 1, 2, 3, 4, 5, right? And the relation R is defined as AB, such that 2 divides A minus B. So we basically have to write the equivalence class of 0. So let us move to the solution part. See, it is given that set A is 0, 1, 2, 3, 4, 5, and the relation R is basically AB, such that 2 divides A minus B. The equivalence class of 0 consists of all the elements of B that belongs to A, such that 2 divides 0 minus B, right? We place 0 in place of A, right? Because we have to find the equivalence class of A, equivalence class of 0, right? So 2 must divides 0 minus B. This means that 0 minus 2 or equivalently B, right, is divisible by 2, right? If minus B is divisible by 2, that means B should be divisible by 2, right? Clear? So B must be even. B must be even, right? See, 0 is also even, right? So the even numbers in A are 0, 2, 4, right? Therefore, equivalence class of 0 will be 0, 2 and 4. Clear? Equivalence class of 0 will be 0, 2 and 4. Clear? Okay, let us move to the next question. 024 will be the right answer. Okay, let us move to the next question. This question says, let n be the set of natural numbers and R be the relation on n into n defined by AB related to CD, if and only if AD is equal to BC. If and only if AD is equal to BC for all A, B, C, D belongs to natural number. So that R is an equivalence relation, right? We basically have to show that R is an equivalence relation. Clear? So again, I am discussing the conditions for equivalence relations. This question have been asked in 2020, right? Okay. So what is the condition of equivalence relation? The function must be reflexive, symmetric, and transitive, right? What is the condition of reflexivity? AA must belongs to R for all A belongs to A. Clear? AA must belongs to R for all A belongs to capital A. That is, suppose we have relation 1, 2, 3. We have set 1, 2, 3. Then for the relation from A to A, clear, to become reflexive, we must contain 1 1, 2 2, and 3 3. Clear? For the relation to be reflexive, right? Now for symmetric, let's discuss for symmetric. What is the condition of symmetric? If a b belongs to R, if a b is belongs to R and bc belongs to R, this imply AC must belongs to R, right? AC must belongs to R. If AB belongs to R and BC belongs to R, this imply AC must belong. This was the condition of transitive. If AB belongs to R, BC belongs to R, then AC must belongs to R. This was the condition of transitive, right? That is, if like 1 2 belongs to 1 2 belongs to R and suppose 2 3 belongs to R, this imply 1 3 must belongs to R. Clear? For the relation to become transitive. Now for symmetric, what is the condition? If AB belongs to R, this imply BA must belongs to R. If AB belongs to R, this imply BA must belongs to R. That is, suppose if 1 2 is belongs to 1 2 belongs to R, this imply 2 1 must belongs to R, right? If 1 2 belongs to R, this imply 2 1 must belongs to R. Okay. So this is the basically conditions for the relation to become equivalence, right? All the three conditions must be satisfied for the relation to become equivalence relation, right? Okay. So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. The question was, let n be the set of natural numbers and R be the relation on n into n defined by AB related to CD if and only if AD is equal to BC. AD is equal to BC for all ABCD belongs to natural number. Show that R is an equivalence relation, right? We basically have to show that R is an equivalence relation. Okay. So let us move to the solution part. Now let's check the relation R on n into n defined by C. If defined by AB related to CD, suppose AB is related to CD, AB is related to CD, if and only if AB will be related to CD, if and only if it is satisfying AD is equal to BC, right? You can see in the question. Clear? So let's check whether it's equivalence or not. So for reflexivity, see, for reflexivity, AB should be related to AB only, right? AB should be related to AB only. Got it? AB should be related to AB only. So in place of CD, we must put AB, right? So AD was equal to BC. So in place of C and D, we must put A and B. So in place of D, we will put B. So AB should be equal to BA, right? AB is equal to BA. We all know that. Clear? 3 into 5 is equal to 5 into 3. Clear? So this is reflexive, right? AB is equal to BA is always true. So it is R is reflexive. Now for symmetric, if AB related to CD, then we can say that AD is equal to BC, right? AD is equal to BC. Implies that AD is equal to BC. If AB related to CD, then CD must related to AB. CD must related to AB. This implies CB should be equal to DA, right? CB should be equal to DA, and it is happening. Clear? BC can be written as CA also, right? BC can be written as CB also, right? Because 5 into 3 is equal to 3 into 5, right? So AD was equal to BC. So we can write BC as CB. Clear? And AD as DA. Clear? So CB is equal to DA. So we can write other way also, like CB is equal to DA. Clear? So if AB is related to CD, then CD is also related to AB, right? Thus R is symmetric. Clear? Right. So AB is related to CD, then CD is also related to AB. Therefore R is symmetric also. Let's check for transitive. For transitive, if AB related to CD and CD suppose related to something EF, then this imply This imply AB must related to EF. AB must related to EF, right? Clear? AB must related to EF. So if AB related to CD, that means we can write AD is equal to BC, right? So our one equation is AD is equal to BC, right? Suppose this is equation 1. And AB is related to CD and CD is related to EF. If CD is related to EF, then we can write CF is equal to D. CF is equal to D. Now using these two equations, we have to show whether AB is related to EF or not. AB is related to EF or not. So we basically have to prove that. Is AF equal to BE or not? AF is equal to BE or not by using this relation, right? So can we multiply this? See, if we multiply this AD into CF, AD into CF will be equal to BC into D, BC into D. Clear? Now you can see that. Can we like cancel out D this side, D this side, right? And C this side and C this side. So AF is equal to B. Clear? We have cancelled D this side, C this side and C this side. So we are getting AF is equal to B. Got it? We are getting AF is equal to BE. That's what we needed, right? We needed AF is equal to BE. So BE. So we can say that AB must related to EF, right? AB must related to EF. Thus we can say that R is transitive also, right? So further conclusion, we can say that R is reflexive, symmetric and transitive. Therefore, we can say that it is an equivalence relation on N to N, right? R is equivalence relation on N to N. Got it? Okay, let us move to the next question. The next question says, show that the relation R in the set A from 1, 2, 3, 4, 5, 6 given by R is equal to AB such that absolute value of A minus B is divisible by 2 is an equivalence relation, right? We basically have to show that absolute value of A minus B is divisible by 2. Again, it is equivalence relation. We know the condition of equivalence relation. It must be reflexive, symmetric and transitive. So we can discuss reflexive again. For reflexive, what is the condition? AA must belongs to R for all AA must belongs to R for all A belongs to A, right? For all A belongs to A. That is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6 must lie on relation R. Clear? What is symmetric? Symmetric says if AB belongs to R, this imply BA must belongs to R. If AB belongs to R, this imply BA must belongs to R, right? Clear? This is the condition of symmetricity. That is, if 1, 2 is lying in the relation, suppose 1, 2 is lying in the relation, this implies 2, 1 must lie in the relation. Got it? 1, 2 is lying in the relation, that means 2, 1 must lie in the relation. Next is, it should be transitive also. And what is the condition of transitivity? If AB belongs to R and BC belongs to R, this imply AC must belongs to R. Clear? If AB belongs to R and BC belongs to R, this imply AC must belongs to R for the relation to become transitive relation. Okay. So all the three conditions must be satisfied for the relation to become equivalence relations, right? All the three conditions must be satisfied. Okay. Clear? Now the relation is defined as AB such that absolute value of A minus B is divisible by 2. What is absolute value of something? Absolute value of x is basically x when x is greater than 0 and it is negative x when x is less than 0. Clear? That is, absolute value must always be positive, right? Absolute value must always be positive. Clear? So we have to basically define the relation R such that A minus B, absolute value of A minus B should be divisible by 2, right? Absolute value of A minus B should be divisible by 2. Okay. Okay, you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. The question was show that the relation R is R in the set A. Set A was 1, 2, 3, 4, 5, 6 given by R is equal to AB such that A minus B, absolute value of A minus B is divisible by 2 is an equivalence relation. So let us move to the solution part. So let's verify that the relation R is equal to AB such that A minus B, absolute value of A minus B is divisible by 2 on A, which was 1, 2, 3, 4, 5, 6 is an equivalence relation. Let us verify. So for reflexivity, for any A belongs to A minus A must lie in the relation R. So absolute value of A minus A is basically 0. And we know that 0 is divisible by 2, right? So R is reflexive. Got it? R will be reflexive because A minus A, absolute value of A minus A is basically 0 and 0 is divisible by 2. Clear? So we can say that R is reflexive relation. Okay. Let us check for symmetric. For symmetric, if absolute value of A minus B is divided by 2, then we know that absolute value of B minus A is always equal to absolute value of A minus B, right? Clear? Clear. Absolute value of minus 3 will be equal to 3, which is absolute value of 3. Clear? Right. So absolute value of negative number will be equal to absolute value of same positive number. Clear? So if B minus absolute value of B minus A is divided by 2, then we can say that absolute value of A minus B is also divisible by 2. So R is symmetric also, right? So R is symmetric also. Got it? So let us talk about transitivity. Now, if absolute value of A minus B and absolute value of B minus C are divisible by 2, right? Absolute value of A minus B and absolute value of B minus C are divisible by 2, then absolute value of A minus C can be written as A minus C can be written as A minus C can be written as, let us subtract and add B. So it was A minus C. So we have subtracted and added B. So A minus B plus B minus C. Clear? Right. Now A minus B was divisible by 2 and B minus C, it is given that absolute value of A minus B are divisible by 2 and absolute value of B minus C is divisible by 2. Therefore, we can say that if A minus B is divisible by 2 and B minus C is divisible by 2, then we can say that, see, if 4 is divisible by 2 and 8 is divisible by 2, then summation of this will be divisible by 2, right? Yes, summation of this will be divisible by 2. Therefore, absolute value of A minus B plus B minus C is also divisible by 2. Sum of even numbers is even. Got it? So R is transitive also, right? So in conclusion, we can say that therefore R is an equivalence relation because it is reflexive, symmetric, and transitive. R is equivalence relation because it is reflexive, symmetric, and transitive. Got it? Okay, let us move to the next question. The next question is we have to show that the relation S in the set A is equal to X. In set A is defined as X belongs to Z such that X is between 0 to 12 given by S is equal to AB such that AB belongs to Z. Absolute value of A minus B is divisible by 3 is an equivalence relation. This has been asked in 2019, right? So this is a similar question as previous one. Clear? So we can approach that question similarly, right? Okay. Again, we need to we have to prove that the relation is equivalence. That is, we need to first discuss about symmetricity, reflexivity. Got it? Then we need to discuss about symmetricity, trick. Then we need to discuss about transitive. Got it? Clear? So what was the condition of reflexivity? A must belongs to R for all A belongs to A, right? And what was condition of symmetricity? If AB belongs to R, this imply BA must belongs to R. If AB belongs to R, this imply BA must belongs to R. And what is condition of transitivity? If AB belongs to R and BC belongs to R, This imply AC must belongs to R, right? AC must belongs to R. This was the condition of transitivity. So all the three conditions must be satisfied for the relation to become equivalence relations, right? Okay. So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let us move to the solution part. The question was, show that the relation S in the set A is equal to X belongs to Z such that X is between 0 to 12 given by S is equal to AB such that AB belongs to Z and absolute value of A minus B is divisible by 3 is an equivalence relation. Okay. So let us move to the solution part. So let's check each property for the relation to be equivalence, right? So S is a set, S is a relation defined as AB such that AB belongs to Z and absolute value of A minus B is divisible by 3, right? On A equal to X belongs to Z such that X is between 0 to 12. So let's check for reflexivity. So for any A belongs to A minus A is equal to 0, which is divisible by 3, right? A minus A 0, 0 is divisible by 3. We know that. So S is reflexive. Okay, S is reflexive. Now let's check for symmetricity. If absolute value of A minus B is divisible by 3, then we can say that absolute value of B minus A, which is equal to absolute value of A minus B, is also divisible by 3. So S is symmetric also, right? If S is reflexive and S is symmetric also, right? So let's check for transitivity. If absolute value of A minus B and absolute value of B minus C are divisible by 3, then we can say that absolute value of A minus C can be written as, we have subtracted B and added B, right? So A minus B and added B, so B minus C, clear, is also divisible by 3 since sum of multiples of 3 is a multiple of 3, right? So 6 plus 12 is equal to 18, which is also multiple of 3. 6 is multiple of 3, 12 is multiple of 3, and 18 addition of the two numbers which is multiple of 3, addition of two numbers which are multiple of 3 is also a number which is multiple of 3. Got it? So S is transitive also. So S is reflexive, S is symmetric, and S is transitive also. So in the conclusion, we can say that since S is reflexive, symmetric, and transitive, so we can say that S is an equivalence relation, right? S is an equivalence relation. Okay, clear? Let us move to the next question. Next question says, let R be a relation defined on the set of natural numbers n as follows. The relation R is defined as xy such that x belongs to natural number, y belongs to natural number, and 2x plus y is equal to 24. Find the domain and range of the relation R. We have to find basically the domain and range of the relation R. Also, find R. Also, find if R is an equivalence relation or not, right? We have to basically find the domain and range, and we also have to check whether R is an equivalence relation or not, right? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, see, let us move to the solution part. Before that, first, we have to check whether the given relation is equivalence or not. We know the conditions of equivalency, which is the relation R, which is defined, must be reflexive, symmetric, and transitive, right? And also we have to find domain and range. What is domain? Domain is X and range is Y, right? Okay, let us move to the solution part. The question was, the relation R is xy such that x belongs to natural number and y belongs to natural number, and 2x plus y should be equal to 24. We basically have to find the domain and range of the relation R, and also we have to find whether R is equivalence relation or not. So let us move to the solution part. It is given that relation R is defined as xy such that x belongs to n, y belongs to n, and 2x plus y is equal to 24. So what will be domain? So let's solve for x. Let's solve for x. So y can be written as 24 minus 2x, right? And both x, y should be natural numbers, right? That is x should be greater than equal to 1 and y should be greater than equal to 1. Now, since 24 minus 2x should be greater than equal to 1, so 2x should be less than equal to 23. Therefore, x should be less than equal to 11.5, right? X is natural number and x should be less than equal to 11.5. Therefore, we can say that x is equal to 1 to 11, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it? Now, for each corresponding x, we can find the values of y. That will be basically range. So, domain is x is 1 to 11. And what should be the range? Now, for each x in the domain, we can find the range. Y is equal to 24 minus 2x. So, y is basically for x, when x is equal to 1, y is equal to 22. When x is equal to 2, y is equal to 20. It will go on till when x is equal to 11, y will be equal to 2, right? Clear? When x is equal to 11, y is equal to 2. Okay? So, range will be equal to 2, 4, 6, 8, 10 till 22, right? So, domain is 1, 2, 3, 4, 5, 6, 7 till 11, and range is 2, 4, 6, 8, 10 till 22. Got it? Right. Okay. Now, let us check whether it is equivalence relation or not. Right? So, for reflexivity, xx must lie, xx must be true for all the natural numbers, and it must lie in the relation R. So 2x plus x should be which is equal to 3x, and it is equal to 24. And after solving this, you will get x equal to 8. So only 8 is reflexive, not all, right? So it is true for x equal to 8 only, right? Not for all x belongs to natural number, right? So it is not reflexive at all. Now let's check for symmetricity. If xy belongs to R, then yx must belongs to R. In general, suppose 1 2 is belonging to 122 is belonging to R, but 22 1 is not valid, right? 22 1 is not belonging to R. So we can say that it is not symmetric as well. So and the transitive is will not always be defined, right? Got it? So in the conclusion, we can say that the domain is 1 2 3 till 11, range is 2 4 6 till 22, and R is not an equivalence relation as it is not symmetric, not reflexive, and neither not transitive, right? So it is not equivalence relation. Okay, let us move to the next question. The next question says the function f is defined from R to R, defined by fx is equal to 4 plus 3 cos x, right? Fx is equal to 4 plus 3 cos x. We have to check whether which option is correct. That is this relation, is this function bijective function, or is it 1 1 or on 2, or not on 2 but not on 1, or neither 1 1 nor 1 2, right? We have to check it. And this question I have been asking here 2022. Got it? So we know that 1 1, and we know the conditions of 1 1 and on 2. What is the condition of 1 1? What is the conditions of 1 1? For each x in the domain of the relation, there must be one and only one image in the range. There must be one and only one image in the range. That is, if analytically you can write, if fx1 is equal to f of x2, then we can say that this implies x1 should be equal to x2 only, right? For 1 1. And what is the condition of on2? Codomain should be equal to range, है ना? Right? Codomain should be equal to range for the function to be on2 function. Clear? And for bijectivity, both the conditions must be satisfied, right? For bijectivity, both the conditions must be satisfied. Okay? Right? So you have 10 seconds to solve or think about this question. After that, we will discuss the solution part. Okay, let's move to the solution part. The function defined as f from R to R, defined by fx is equal to 4 plus 3 cos x, right? So the answer will be D. That is neither 1 1 nor 1 2, right? D will be the right answer. Okay. So let's move to the solution. See, the cosine function cos x takes the value, that is range of the cos x, we know that is from -1 to 1, minus 1 to 1, right? Clear? So fx will take the value, that is minimum value of fx can be 4 plus 3 minus 1, which is 1, and maximum value can be 4 plus 3 into 1, which is 7, right? This means that the range of fx is in the closed interval from 1 to 7. But for the function to be onto, codomain is equal to range. Codomain is R, but range is from 1 to 7, right? So we can say that it is not onto, right? Clear? Codomain is not equal to range here. So it is not onto function, right? Also, since cos x is periodic, we know the graph of cos x like this one, right? Clear? The graph of cos x, right? So it is periodic. When you will draw any line parallel to x axis, clear, you will get many points. Clear? So corresponding to a particular value of y, there are many x, right? Corresponding to a particular value of y, there are many x. Got it? Therefore, it is not 1 1 as well, right? Therefore, it is neither 1 1 nor onto. Got it? Okay, hope you understood today's lecture. We have done previous questions of CBSE, and hope you understood and hope you liked our lecture, right? Thank you so much.